Thank you very much. Timely because as of 2 days ago, we have the first two spacecraft coordinated mission at the moon. Sorry, Maria. This is the Artemis mission. Two spacecraft, it's a reconfigured constellation of what was originally the Themis constellation. That was 5 spacecraft that were launched in 2005. Thank you. And 2007, I'm sorry. In February 2007 and performed admirably beyond its original lifetime of 2 years. Numerous papers have been written and resolved the question of where do substorm onset and the aurora eruption during substorms in the Earth's magnetosphere start from. It turns out that after the 2-year mission, the outermost two spacecraft, the spacecraft were designed to be aligned along the Sun-Earth line every 4 days and capture, basically time the evolution of plasmas from one spacecraft to the other, from very close to Earth, about 12 Earth radii, all the way to about half the distance to the Moon, about 30 Earth radii. Beyond the primary mission, though, the two outermost spacecraft would experience very long shadows, and something had to be done. NASA never allows you to think beyond the main mission, and so, but we were kind of thinking in the background and devising plans on what to do after. So Artemis is what happened after. Artemis was put together in response to saving the two spacecraft from the long shadows, the 8-hour shadows they would experience. And along the way, we realized that significant planetary objectives could be achieved from the orbits that they would attain. I will describe those objectives and the status of the mission as of today. The spacecraft look like this. They're spinners. They're about a dishwasher size large, 1 meter on each side. And they're spinning with a 3-second spin period, and they carry a suite of 5 instruments. The spacecraft are identical. So the 5 instruments on each are measuring particles and fields at the location of the spacecraft. So these 25-meter long booms, from here all the way to that wall, they are measuring the electric, the potential on the tip of each boom, and by having 2 boom pairs on each spin plane and 2 axial pairs at about 3.5 meters each antenna. Along the spin axis, we measure the electric field at the location of the spacecraft. Then there is the magnetometer booms that carry magnetometer instruments, AC and DC here, the search coil and the flux magnetometer respectively. And then there are particle detectors, the electrostatic analyzer and solid-state telescope measuring particles from a few eV up to tens of kilovolts for the ESA and up to MeV range for the SST. With those, then you have comprehensive plasma and fields measurements at each location. Now, here's the arrangement of the spacecraft. You would do nothing to them. These are the orbits, and X points towards the Sun in a Sun-Earth fixed frame, the GSE frame. And these are the inner 3 spacecraft, and by year 3, spacecraft P1 and spacecraft P2 will be far away in line of apsides due to the differential precession from the other inner 3 spacecraft, so useless for the initial science, but also they would experience the long shadows. So we took these 2 spacecraft and decided to devise a way, thanks to JPL mission design, to put them around the moon, creating the Artemis mission. And Artemis was a fantastic opportunity to perform heliophysics science initially. We thought just that. To do science in the magnetosphere, that is, understand the 3-dimensional size of these plasmoids emitting during time of storms, acceleration, reconnection in the solar wind from 2 spacecraft point of view for the first time, and more spacecraft if you put together WIND and ACE out there. And finally, to understand the lunar wake, how the moon is interacting with the solar wind, carving a cavity behind it, a pristine laboratory for plasma physics, but also tied together with the lunar exosphere and the lunar regolith. As a bonus, because we have long-term observations, solar cycle timescale from these stable orbits, we would use the spacecraft as a solar wind monitor over long timescales. The orbits that were designed initially just for heliophysics point of view, they were going up to the moon from their initial location by circuitous trajectories, the kind that Maria described a little earlier, after 3 translunar injections for P2 and 2 translunar injections for P1. These orbits take very little fuel, but take a long time. So it would take about a year. It took about a year for the spacecraft to arrive from their initial orbits to roughly the lunar orbit. And the plan was to capture them there in these metastable points between the Earth and the Moon for the first time. These were used for the first time operationally by any spacecraft. Artemis stayed there for 3 months on either side of the Moon, and for about 6 months on the same side of the Moon towards the Earth, achieving a wide range of interspacecraft separations from 60,000 to 120,000 kilometers apart, and studying these plasmoids and reconnection dimension. But as of 2 days ago, both spacecraft were then inserted into lunar orbit, and the orbits were designed again to achieve a very wide range of interspacecraft separations. What I'm showing you here is the orbits month after month. One is in a retrograde, the red one, the P1, is in a retrograde orbit, and the P2 is the blue one, is in a postgrade orbit. As a result, the differential precession between the two gives you, over a period of 2 years, a very wide range of interspacecraft separations to do really nice studies of the magnetotail and solar wind and the lunar wake. But notice, these are orbits that have a very low periselene, and we could use that to do some unique planetary science. First, let me prove to you that the data is coming back nicely and giving us a new insight into lunar wake phenomena. These are several papers that have been written already from the first phase, the Lissajous phase, during a long-range crossing of the lunar wake about 4 RL away, and the papers were written in Space Science Reviews by Halikas et al., and simulations are being done currently. You'll see, in fact, a poster by Andrew Poppy later today or tomorrow, so in this meeting. And so the instruments are performing admirably, and we can use them for more than just doing heliophysics. The kind of planetary objectives that we then propose to the planetary vision to address have to do with the following. Understanding the exosphere. These instruments that are measuring charged particles are extremely sensitive. Measuring one particle at a time, they can give you a very good, extremely good sense of the particle fluxes at distances beyond what Kaguya had observed, all the way out to the previous flybys by the WIND spacecraft. So by tracing those particles back to the exosphere and the surface, we can get a sense of where those particles are coming from, and by analyzing the behavior of the particles in the external fields, we can get a sense of their mass and therefore composition. In addition, we're measuring locally, and for the first time in the lunar environment, the electric fields. Not only that, but we have an electrostatic analyzer that can measure electrons that are scattered off, that are reflected off the surface, and perform the same analysis that Lunar Prospector has done to understand the electric field at the surface. So now you have two spacecraft that are giving you information of the electric field both at the location of the spacecraft all the way down to the surface, and as a result give you an extremely good information on how the dust that we heard about is being lofted and where is it carried away from the surface due to this external electric field. So we really feel that the local measurements of Artemis, but also the collaboration with LADI will be extremely powerful in the years to come. For this reason, we're preparing the Artemis orbits to line up their periapsis passes when LADI will be up in space at the time of launch. Moreover, we're carrying very accurate magnetometers that are identical on the two spacecraft and can be very well cross-calibrated. Now, this is the first time that this is being done. It's been tried before in the Apollo times by using the Explorer 35 as a distant spacecraft and the Apollo submodule closer to the surface. But what Artemis offers is the identical instrumentation and from nearby locations. So the solar wind you're measuring is exactly the solar wind that is impinging on the moon. And thanks to these measurements, we'll be able to infer the induced field at various distances from the surface because we can perform these measurements as a function of frequency and look at the response as a function of frequency, which actually gives you, which actually can be inverted to give you the response as a function of depth. And notice in the old results that we're performing similar analysis by Hood et al., the most difficult, the highest uncertainties in understanding conductivity as function of radius occur very close to the surface and very deep inside the core. These we can get to by studying frequency, studying periods, tens of minutes to hours apart. We can do that. These are the aliens coming, yes. And we can do that with crossings of Artemis through the distant magnetotail. These we can get to by looking at the correlative measurements of electric and magnetic field on each spacecraft. And so these are the measurements on P1 and P2 that will be used as they're passing by periapsis to study the electromagnetic induction close to the surface. And then when you use the contiguous traversals of periapsis with two spacecraft, one after the other, you can stretch out that time and then use multiple passes to get to the deep interior sounding. And so the particle instrumentation in Artemis can be used in tandem with LRO's crater instrument. I'm glad to see the LRO folks here, and we can talk a lot more about this because where our energy range finishes at the MEV, that's where the crater instrument starts. So it's a very nice collaboration that can happen there. To give us an understanding of the lunar space environment. I mentioned the correlation with LADI, and then because these orbits finally are long-term, have long-term stability, they can last for many years, solar cycle timescales, then we have a chance of overlapping with some of the upcoming lunar network nodes that are being envisioned. These are the periapsis of the spacecraft of P1. Each dot is an orbit. An orbit is about 26 hours. And so this was about a week. This is about a month. So every month we get a very low periapsis here. These are the periapsis of P2. These are our conjunctions with LADI. If LADI launches on time, P2 will be in place to welcome it there. If LADI launches at the extreme other side in October, P1 will be in orbit to welcome it there. So we have good correlations there. These are some of the crustal anomalies, anomaly conjunctions that will happen with P2 periapsis, P1 and P2 periapsis. And finally, the status is that all our instruments are green, and we are being currently, the cross calibrations are being put in the nominal database, so everybody can take a look at the data. So a heliophysics mission turned planetary and looking really very, very good and with a lot of exciting analysis in many years to come. Thank you.
Congratulations on a really creative use of the heliospheric missions for planetary science. Do we have any questions?
Valery Tinishev, University of Michigan, you mentioned something about tracing particles back, but the question is, what is the characteristic time of scattering of, say, pickup ions on perturbation of magnetic field, for example, outside of the magnetosphere? What is the characteristic time, and how it's compared with gyro frequency of light ions?
Characteristic time of what?
Characteristic time of scattering of pickup ions on perturbation of magnetic field when the moon is outside of the magnetosphere.
Oh yes. So the approach there, and the approach that people like Menelao, Sarandos are taking, and the Kaguya folks have taken, is to trace those particles subject to fields that are thought that are measured locally and are thought global, essentially. So the particles will be gyrating around, and you can do ballistic trajectories of those particles subject to locally measured fields.
Yes, and that's why I have the question. What is the relation? I mean, is scattering, characteristic scattering time of pickup ions faster or lower than gyro frequency?
No, the scattering timescale of these particles are, the collision timescale of these particles is extremely long compared to their, to the gyration.
So is it hours, minutes?
Are you talking about the solar wind spatial inhomogeneities?
Oh yes, on perturbation of magnetic field in solar wind.
Now, typically people do not address this question. But for the first time, we will be able to address it by measuring the scale size of solar wind clumps, because we do have spacecraft, 2 spacecraft there. But the gyro radii of the particles we're talking about, argon, for example, or potassium, they are order of a few lunar radii. So, and they go down, if you're talking about proton gyro radii, are the order of a few hundred kilometers in the solar wind.
Okay, thanks.
One more question? Over here.
I think the scattering time scale is days and the gyro period is seconds, so I think it's 5 orders of magnitude different and not important.
Yeah, this kind of collision scattering, for example, is a very long time scale. But inhomogeneity is something we can address.